Myself, Srinivasan, working as a faculty in the Department of Mechanical Engineering at Shishanma College of Engineering. I'll be talking about single-layer Perceptron and multi-layer Perceptron using Python. The single-layer Perceptron and multi-layer Perceptron, these two lectures were already discussed the class. And what are the problem I solved on single-layer Perceptron and multi-layer Perceptron has been explained using Python code. I have used School Collab, and here report NumPy. That is NumPy is basically a library which is used for numeric calculation. The input data are given over here. This is the input feature 1 and 2. The input data is 1 and 2. And the predicted, actual one is 1, and the weight is 0.2 minus 0.5. Bias is 0.1. The learning rate is 0.01. Okay. So we have run for the 3 epochs and the numerical problems that we have solved. And the epoch is basically a iteration of one training data set. And what we are doing in net input is basically your summing over there. W and weight and the input features are multiplied plus added with bias term over here. And the summation is happening here, and the predicted one is basically using the activation function. Here we have used here is step function. Okay, so the net to input is greater than 0, then it is going to be 1. That it is less than 0, that is going to be 0. Okay, so this is a condition we have used here. The error is basically the difference between actual minus predicted one. Okay, so till we get the value as the predicted one is same as we will run the till we get the predicted one is same as the actual one. Okay, so till the time we update the weights. In the first epoch, if you look at the net input is minus 0.7, it is less than 0, then if it is less than 0, it is going to be our predicted output is 0, the error is 1, okay, because the actual minus in predicted one is 0, then you get the error will be 1. So what are the weights updated in this case are as follows. On epoch 2, we have got minus 0.1. Here also, since it is going to be less than 0, then the error is going to be 1. On the next epoch, we got more than 0, that is 0.05. The predicted output is 1, the error is 0, the updated weights are 0.4 minus 0.01. So, and updated bias is 0.30. So this, whatever we have solved in the numerically, the same as in the code. The output is same as given by the code. Next problem on multi-layer perceptron. Here we discussed XOR problems. Okay, as in as we have seen in the theory, and the non-linear, XOR problem cannot be solved by single-layer perceptron because you need two bounded lines, and you need to solve that. So we can use this multi-layer perceptron here. And we use NumPy as we discussed in the SLP, and the sigmoid activation function, and the derivative of sigmoid activation is necessary for the gradient the weight updates. So these are the input values of this, and 0, 0, 0, 1. There are 4 sample I can say 0, 0, 0, 1, 1, 0, 1, 1. Okay. So in XOR problem, either one should be 1, and remaining the true values are going to be 0. So this is a target output. Okay. So then randomly we are initializing the weights of W1, B1, W2, B2. So W1 is basically the input to hidden, and W2 is basically input to output. So the architecture with that we have used in multi-layer perceptron is 2 input and two neurons in the hidden layer and 1 output. Okay. So these are the learning rate we have used 0.5, and epoch is 5000. So as we reduce the epoch, then there will be more, and you have to optimize that the number of epochs. Okay. So I have tried and 1000, 2000 and all, and I got very close result when I increase the epoch 5000. Okay. So we have to adjust the hyperparameters over here. Okay. So then here we have to here we have to update the weights, and first we have to do the forward propagations, feed forward propagation, feed forward network, and it is summation activation, both will happen over here. Okay. So once we get the error, then we have to update the weights. Okay, we have to update the weights, and these are all the gradient descent algorithm is used over here. So we have got the sigmoid derivatives. Okay, and we are updating the weights in the back propagations. So the final output what we have got is 0.003 and 0.974 and 0.974 and 0.028. Okay. So the predicted one is around 3. There will be 3 decimals will be there. Okay. And the original output is 0.110. And what we have got in the predicted output is 0.03 and 0.97 and 0.97 and 0.0, which is very close to the real one. Okay. Thank you.